Perfect. So that is the top of the hour, and I want to welcome everyone to today's e-talk presented by Russ Renzes on atomic layer etching for better quantum device performance. Before I hand it over to Russ, I want to let you guys know that we will be using the question and answer feature of the chat today. So as the talk goes on, go ahead and put your questions for the speaker into the question section, and we will make sure to get to as many as we can at the end of the talk. If you have any technical issues, you can put those in the general chat, which I won't be checking as much for questions during the specific question and answer section. So there's an additional professional development webinar on the 20th. So go ahead and register for that. It will be about a week from today. And we have a brand new AVS Thin Films LinkedIn group, so scan the QR code on your screen and join, and you will see all of our posts on everything Thin Films division. JVST is soliciting papers for a special collection on ALD and ALE. Submit by November 1st. And then AVS 72 is coming right up. Call for abstracts is due next Monday, so May 18th. So go ahead and do it today and just get that off of your plate. And we will see you in Pittsburgh in November. It is going to be a fantastic event, and you will get to enjoy all that the AVS community has to offer. And with that, I'm going to hand it over to Russ.
Awesome. Well, let me get the screen sorted, and we will be off to the races. All right, how's that looking? We good? All right. So thank you for having me. I'm Russ Renzis. I'm a research faculty member at the University of Nevada, Reno. I'm also director of the Davidson Foundation Clean Room. Before coming to Reno, I had kind of a odd career. I actually started in surface science, doing heterogeneous catalysis, bimetallic nanoparticles, things like that. Worked on a wire and cable company during the Great Recession, which I don't recommend. Uh, and a couple startups later, I ended up building the fab for Rigetti Computing, which is a quantum computing company. Then it was a very, very small company. We rented out a warehouse and with damaged floors essentially, and I had to turn that into a clean room and a fab and buy all the tools, hire all the people, develop all the processes. And I left there a little bit ago, but now that company's publicly listed and doing really, really, really well. And that's really where I learned a lot about about the quantum side of things. Later on, I worked for Oxford Instruments Plasma Technology for about 3 years on the semiconductor processing equipment side. And there, of course, a lot of interest in atomic layer etch, atomic layer deposition. Many of you know them as a tool vendor. And at Oxford, I spent a lot of time in my sort of very public facing role. I gave a lot of talks, went to a lot of places, and I'd spend a lot of time thinking about, well, if you have these systems, these ALD systems, these ALE systems, what then? What can you do with those systems that's going to make somebody care, that's going to make a device better? And I think it was a really interesting experience spending those 3 years, because it's not often that as scientists we get to sit back and think kind of at the macro scale and look at ecosystems and look at needs and look at unmet needs on a technical level. Certainly there's a business component to that, but I was very much on the technical side. And so during that time, I spent a lot of time focused on what the real problems are and what these tools can do for those problems. And so today I hope to share with you not only some of those insights from my time at Oxford Instruments, but also now that I've been in academia for about 2.5 years, and I should be really clear, my research group only been operating since August, because I started with an empty clean room, and as many of you know, it takes a while to get tools and tables and everything else, facilitate things. So we have some of our first results. I'll be sharing results from our first paper, as well as a little bit of preliminary data from what we hope will be our second or maybe even our third paper. And we're really at the starting point. So it's a little bit unusual in that I kind of came to the university after a longer career in industry. Um, but I think it's interesting. It gives me a lot of insights. The one thing that I do run into a lot is I found in industry, I was always told you're a little bit too fundamental. And then in academia, I'm always told I'm a little bit too applied. So hopefully for a lot of you on this call that might be riding that same line that I've always been on, this will be very interesting to you. So here we go. Let's talk about atomic layer etch for better quantum devices. First thing, a little outline here, and you can see beautiful Reno, Nevada. If you're wondering why I'm in Reno, it's because I like to ski and kayak and hike. We are about 4 hours from Silicon Valley, just northeast actually. So first, we're going to do an introduction to quantum devices, talk about quantum devices, what they are at kind of a high level, and what that means to us really as AVS members, not so much what that means to us as investors or what have you, but as AVS members. Then I'm going to talk about atomic layer etch. What is it, how, and why? And we'll get into some specific examples around superconducting qubits, ALE processes for that, what's happening in that community, and quantum photonics. So what is quantum? At a very, very high level, I think of quantum as anything in the quantum devices field, which is kind of the first three here: computing, communication, sensing. Fundamental science can be all sorts of things, uh, all sorts of stuff. But on the devices side, we're using a quantum effect to do the measurement, right? Or to do the computation. We are exploiting some kind of quantum effect. What that means in practice in the computing sense is that instead of having these sort of binary systems where we use capacitors and we have memory elements and the transistors, this physical switching element, quantum computing, we're really taking advantage of entanglement and interference. The qubit itself is our memory element. What that memory, that state is defined as a complex number. When you get entangled qubits, it's this tensor matrix and it expands hugely and you get this huge state space. The gates themselves are really microwave pulses or lasers, or there's a few different ways of doing them. In superconducting qubits, they're microwave pulses. So the gates are actually pulses. The qubit is stored in this, as we'll see later, anharmonic LC resonator. What that means from a business perspective or the outside world, I guess, is that there is potentially for certain kinds of problems, a subset of problems, a significant speed advantage. Most famously, Shor's algorithm, which could potentially do decryption if we have way more qubits than we have today at way higher quality. Now, I'm a material scientist by training and by interest. So what I really care about is what can I actually do to make that better? And so the defining thing that I think about with all of this, although yes, I do know a little bit about the application side of things, is, gosh, when I was working on classical types of devices, my signal to noise might have been a whole bunch of electrons or photons, whatever it was. If I lost some of them, that's bad, but as long as I'm above signal to noise, I'm all right. In quantum devices, it's not just even their presence in some cases. It's not a matter of even losing the photon. It's does your microwave photon interact with its environment in any way that's not what you want? So any bath of states, anything, any two-level system defect, any little fluctuator at the nanoscale, just the smallest perturbation, if that's resonant with the frequency of your qubit, it can cause decoherence or it can perturb the state. So in a sense, as material scientists, yes, quantum is a great application, but also it's a really interesting model system because as people that are interested in things that are happening at the atomic scale, I want applications where what I'm doing is going to matter. And in the atomic layer etch space, I want applications where the structure of things, just small perturbations and contaminations, can be manipulated to improve the performance of the device. And so quantum devices are great because they're affected by everything, even when you don't want them to be. There are lots of types of quantum devices. We'll call them modalities: superconducting circuits and quantum dots and color centers, trapped ions, photonic quantum computing circuits. There's other types as well. It's any kind of two-level system, really. They use a wide range of materials. So what is different about quantum device fabrication? Generally speaking, not a whole lot. we might be using a little bit different materials. Our metals might be different. In superconducting qubits, we can't use copper vias in most cases because it's not a superconductor. So if I want to transfer superconducting information or information without any dissipation, I need to figure out how I can get a superconducting via that's of a material other than copper. So that might need to be niobium tinitride or something I can deposit by ALD or something like that. Um, but you'll notice, for better and for worse, it's a pretty wide range of things as well. It's not like we're going to figure out a deposition or an etch for just one material and be good to go. And what's common across all of these modalities and all of these materials is that they all have lossy surfaces. They're very, very, very sensitive to what's going on in the surface. There's a lot of evidence of unwanted strange interactions. In the color center space, which I'll talk about towards the end of the talk, we see the zero phonon line for silicon carbide color centers wander around. And if you look at the y-axis here, these are on human timescales over the course of an hour. Superconducting qubits, people will report coherence times, but as everyone in the community knows, those coherence times fluctuate wildly. Now, this is for a device that's at 10 millikelvin, and still the lifetime, the coherence time, the amount of time that it can maintain its state fluctuates wildly because there's some kind of long-lived interaction, something that is out there that our qubit can interact with. Single photon emitters, the whole idea is that you've got totally indistinguishable photons emitted over and over and over and over again, but they're not indistinguishable because as we see over the course of, again, human time scales, we see the emission wavelength wander around. So there's something going on in the system. There's a fly in the ointment. Okay, so let's talk about atomic layer etch now. We're gonna go back to our etch, and then we're gonna go to does this actually matter? So in AVS, I think most people are going to know what plasma etch is. I obviously don't know who all is on the call. At a very, very high level, it's a chemical reaction between some kind of solid material, substrate or material, metal, dielectric, whatever, and some kind of gas phase etchant. And it produces a product that hopefully is volatile. That could be a chemical etch. So if you're talking about just photoresist, you're ashing oxygen in a plasma, it produces radicals, and those very, very reactive radicals will form CO2 and water. Great. SF6 does similar work with niobium and silicon. For instance, you can get niobium tetrafluoride, pentafluoride, I guess, SiF4. You can get these products that are volatile. Awesome. Chemical etches, you have to worry about selectivity, passivation, safety. Obviously, chlorine can be a bit dangerous. It's less sensitive to bias, tends to be a more isotropic, all-directional etch. Physical components, we also can use argon, ionize that in the plasma, and use that to sandblast things off. You can do that with other ions as well, anything that's responsive to an electromagnetic field. However, when we do this, we are not cleanly just removing layers. We're dumping energy into an interface. So no matter how nice that interface was before we began dumping energy into it, when you start contaminating this thing with chlorine and fluorine and argon, and you're just smashing stuff into it, you are creating a damaged layer that's typically anywhere from 3 to 7 nanometers of the surface. It can be more, it can be less, and that damaged layer will depend on how much energy you're dumping into the interface. Remember, with these quantum devices, incredibly sensitive to loss, to any kind of perturbation. This isn't good. These interfaces look a lot like kind of the big scary boogeyman of the quantum field, which is these two-level systems, these glassy amorphous systems. Not great. There's a lot of evidence that RIE causes significant surface damage. Way back in 2006, people are looking at how the effective lifetime of a carrier, it decreases as RF power of an etch increases. So the more energy you dump into the surface, the worse the carrier lifetime is. This is kind of studied in a lot of areas. We know the higher the bias is, the more that we'll see, and the thicker the amorphized layer is at the surface if you're just doing like a simple argon sputter. Same thing, you put more chemical energy in, that damaged layer gets thicker. So, okay, well, what do we do about it? That's where atomic layer etch comes in. So the interesting thing about atomic layer etch to me is this decreased subsurface damage. This damage layer could be reduced. Yes, there are other potential advantages. Maybe you want to etch 3 nanometers. And I've had situations where people ask me about how do I etch 3 nanometers of a thing. That's really hard to do in a timed etch. Atomic layer etch is going to work really nicely there. Cyclic, really well-controlled etch rates, awesome. Um, Maybe I'm worried about surface roughness. Atomic layer etch, typically smooth surfaces. Awesome. In many cases, that's really, really important. However, what I tend to think of as the major advantage of atomic layer etch, and certainly why I'm very, very interested in it for quantum applications, is because of this reduced subsurface damage. So we're going to try to find a way to etch while putting less energy into our surfaces. Generically, the approach we're going to use is we're going to modify the surface layer, weaken it somehow, hopefully without any kind of continuous etch. Then we're going to remove that now modified layer. If we can do that selectively without affecting the underlying material, we can hopefully minimize the damage that we're getting and improve the performance of our devices. This is a really generic process. If you start thinking about it, there's a lot of ways of doing this. You can modify it chemically, you can modify it maybe with all sorts of energy, right? Anything that can amorphize or perturb the layer in some way, change its structure and chemistry, is potentially a sufficient modification as long as it's self-limiting in some way. Anything that can then remove that layer selectively to the underlying layer, if it's heat, whatever, another chemical, could work. So ALE as a field is a really, really wide-ranging kind of generic process. There's a lot of ways of doing it. And it's been shown in a really wide stretch of devices to improve device performance. This is an early example in 2007 on indium phosphide Schottky gate diodes where they use chlorine and neon actually. Usually you'll see argon, but in this case neon. And ALE was shown to increase the drain current density and Hall mobility, decrease gate current density. They saw a big performance increase. Similarly with these aluminum gallium nitride devices, Schottky barrier diodes, they're able to reduce leakage current. And I want to call your attention there to the images kind of on the lower left. You can really see this defective amorphized layer is much thinner when they use the atomic layer etch process. So that really matters for real devices. And my favorite example, Neha Mahuli, she was a postdoc in Steve George's group, which is any of you in the ALD space know is a really important research group. They've done incredible stuff for a long time. Well, she's at Amazon now in the quantum team, and they were able to show that using an atomic layer etch, atomic layer deposition process in which they took the native oxide that's formed after their typical etch of an aluminum device, remove that damaged native oxidized layer with atomic layer etch, and then in situ grow back a higher quality ALD oxide, they were able to double the coherence time of superconducting qubits. So there's clearly something here. Clearly, atomic layer etch has a place in quantum device fabrication, as well as the fabrication of all sorts of other devices. So how does it work in the most conventional way? The most common way that we do this is what we call anisotropic or directional ALE. There's a lot of other types, all chemical ALE with precursors and other things. I'm not going to talk about those very much. They are very interesting and they're no better or worse than any other kind. But today we're going to focus on anisotropic directional ALE. At a high level, I just have my surface. I show that as a surface scientist, I always like to point out that actually the surface is the hardest part to remove in anything because, of course, when we cleave any material, the material relaxes back, right? You get back bonding or oxidation or other effects going on where that surface is trying to stabilize itself. So we have to weaken that surface somehow. Interestingly, actually, if you look into catalysis type work, the second layer tends to be a little weaker, and there's like this kind of accordion-like of sequence of bond lengths as you get into the bulk that eventually evens out. Anyways, so you dose this thing, you do some kind of modification. Maybe it's chlorine. The most common process, kind of the canonical ALE process, is chlorine, argon for silicon. So say you have silicon, you chlorinate that surface, You form silicon chlorine complexes at the surface. Uh, there is not enough chemical energy to create a volatile product just yet. So then you remove excess chlorine from the gas phase, and then you go ahead and you use a little bit of argon with a bias, and you remove those surface complexes. These are cartoons. They are not meant to be, this is not molecular dynamics simulations. They are cartoons. Then you purge it and go again. If you look at the upper right, that's kind of generally how these things work. You leave the inert etch gas flowing, you leave the ICP power on through all your dose, purge, etch, and second purge. You dose during the dose step, purge it out a little bit. You etch during the etch step, so you just have inert gas in there, and you turn on the bias, and that's how it works. Fairly straightforward in most cases. The way that we think about this process from a figure of merit point of view is something called synergy. So in synergy, we think about the etch per cycle. How much did we remove with each of these cycles? And then let's subtract out what happens if we just run the dose step over and over again. That's alpha. What happens if we just run that etch step with no chemistry, no modification over and over again? That's beta. So how much are those steps contributing? And then we really look for synergies that are in excess of about 90%. Typically, we see that there's what we call the ALE window as a function of ion energy. So as we increase ion energy, as long as we have enough adsorbates, enough of a modified layer, it's enough to modify the whole surface. At first, if your ion energy is insufficient to remove that modified layer, you don't see any etching. Then, when you have enough energy to remove that modified layer, but not to do any kind of bulk sputtering or physical etch, then you see hopefully a nice flat, we call it the window region in your process where the etch per cycle is pretty constant. Then when you get to a high enough ion energy, you get into a physical sputtering regime. This has been shown over and over and over and over again to smooth surfaces. And you can see a really nice example that Lamb published, I guess, gosh, 8 years ago now, where on silicon chlorine, that canonical process, they show that the RIE process, they get a surface roughness afterwards of 2.3 nanometers. When they use an ALE process, that's much reduced. Another just example from work up in Glasgow, gallium nitride, they look at, all right, what's their melting point beforehand? Gallium nitride, pretty tough to just physically sputter this. It's a pretty robust material. Gosh, if I can fluorinate it or chlorinate it or brominate it, that makes at least the gallium component much easier to remove. So they go through, and in this case, they're using HBr, and you can see that nice ALE window. At first, relatively little etch. Then once they have enough full coverage, there's a window where the etch rate is relatively constant, right? And then when they get above that, they start to get into a physical sputtering regime. They have very, very high synergy, and they also showed, I don't know if I have it here, but a really nice reduction in surface roughness. So that's ALE. Great. Okay. ALE and superconducting qubits. Let's talk about what we care about. You already heard about the example from Amazon. Pretty cool stuff. So let's talk about actual superconducting qubits. Why is superconducting qubits in particular an interesting application for ALE? So on the left here, I'm showing an image published from IBM's group some time ago of kind of a generic superconducting qubit. And these wiggly lines are the resonators. Resonators have a non-dispersive interaction with the Josephson junction, the qubit itself. And the qubit itself is an anharmonic LC resonator. Josephson junction, you can kind of see it on the right, is a tunnel barrier, typically aluminum oxide, aluminum. The oxidation is kind of done in situ. In most cases, people will do what's called double angle evaporation. They will create this sort of lift-off mask structure, tilt the wafer one way, do a directional deposition, typically with electron beam evaporation, oxidize that surface, flow oxygen in some controlled manner, tilt it the other way, and then by the shadowing pattern of the masks, able to get this kind of overlapping deposition all in situ. So really, it's kind of this sort of native oxide. Typically, that oxide is anywhere from 1.5, 2.5-ish nanometers thick. You can make it a little bit thicker. In most cases, people do not. The thickness of that oxide, the area of that overlap junction determines the Josephson energy, how much energy is in the junction. And that's tied to the inductance, and the anharmonicity, ultimately, of the qubit. There's a lot of different families of qubits. The most common is the transmon, but by manipulating really the ratio of the capacitive piece of the circuit to this inductive piece of the circuit, you can control the qubit properties. Um, super. These things have lots of sources of loss. Setting aside deposition-related sources, you can see there's going to be a native oxide on that aluminum. There's going to be interfaces all over the place. Electromagnetic fields are participating in everything. So let's think about, well, which sources of losses do we care about? All right, I'm going to separate this out to three interfaces: metal-air interface, metal-substrate interface, and the substrate-air interface. Electromagnetic fields are participating in all of this. Now, you don't get a ton of loss in the superconductor, as we shall see, but those electromagnetic fields are participating in all of these different interfaces. So the simplest way to look at this loss is through the measurement of what's called the quality factor. The quality factor is proportional, more or less, to coherence time, which is ultimately the figure of merit that we really care about. Resonators are much easier to make, simple meandered structures. So a lot of the materials type work is really done at the resonator level. This quality factor, just the sharpness of your resonator's peak, it depends on the design, QC, but also on the internal quality factor, which is really the part that's due to materials loss. So as material scientists, that's the part that is kind of our responsibility in a sense. So they're just looking for this sharp peak. How much does it diverge from what they designed? If it diverges a lot and it's much lower and flatter and wider and broader, a lot of materials loss is going on. All right, well, we can separate this out. We'll separate it out as the participation ratio of these electromagnetic fields, which depends on design, of course, in the substrate, the superconductor itself, and the surfaces. And then a quality factor for those, an inverse loss tangent. In practice, this is totally dominated by the surfaces. And so it's just these three interfaces we care about. Now, let's think about these interfaces. For the purposes of ALE, the metal substrate interface is really something you control during the deposition process. So that's not really us. We're going to care a little bit about the substrate air interface and the metal air interface. These all have different proportionalities. These change depending on device design and can be manipulated. But the part I really want to call your attention to is that while before I was kind of showing that metal air interface as being, well, it's the top, right, of the deposited metal, actually, because the fields are concentrated at the sidewalls, at these corners, something like 90% of the loss at the of the participation, at least, in this metal air interface is at the sidewalls. So we want to find a way to improve this. So at our group, one of the first projects we took on was to look at this for tantalum. I'm going to move a little quicker than I normally do just because I think I'm so used to giving hour-long talks, and this is supposed to be 45 minutes. Well, we're really interested in whether we can use ALE to improve resonator performance. There's no ALE process for niobium and aluminum, which are two of the very, very common materials. There is previously published, I believe by Lamb, an ALE process for tantalum, but it requires chlorine, and it was not really done specifically for the qubit community. We don't know whether tantalum, it has a couple different phases in the superconducting qubit community. We care very much about the alpha phase, not so much about the beta. We don't know whether those are affected the same way by ALE processes. There's a bunch of other stuff we don't really know. But what we do know is that we want to have some selectivity to silicon as well to control our overedge. So what chemistry should we pick? Well, you have all these compounds. They all have different melting points, right? Great. We want a process that's pretty stable at a manageable process temperature and pressure. We want it to be easily removed with argon. So we want something that's pretty easy when we make that modified layer to remove. We want something ideally, something that we dose that's a gas at room temperature. Other people can do liquids. Our system is just for gases. We want some decent selectivity to silicon and photoresist. At UNR, university state is essentially new to device fabrication. We want something safe. We don't have some of the EHS controls that they have elsewhere. We're new to this as a state. And we want something that's cost effective, which has come up a few times when gases cost $17,000. So first things first, well, I want something that's going to operate in a pretty manageable temperature regime. I don't want it to be too volatile, something which is going to be chemically etched. So I'm going to kind of ignore stuff where The melting point is super, super low. This is a first cut. I know melting point's not the best way to go about it, but we're just trying to get started here. Cool. We've come up with some nice candidates. Well, again, safety, UNR is not been doing fab for a super long time. Our fab's only been open less than a year. So we're going to ignore chlorine, bromine, and iodine. And that leaves us with fluorine. All right, well, let's do that. But the problem is, how are we going to get selectivity to silicon? We don't just want to get through our material and then start blasting through the silicon in the system. So what we're going to do is we're going to consider adding hydrogen. So this is a little bit different from the ALE I described before because we're actually going to get polymer formation and some deposition in some cases, right? So if we want to control the amount of spontaneous etch of silicon afterwards, we're going to need to control the amount of free fluorine in the gas phase during the dose step. So we're going to do that by adding lots of hydrogen to form HF. So luckily, there's some really great work out there. Kuzmenko and his team did some really nice stuff doing selective atomic layer etch of aluminum oxide, aluminum nitride, and hafnium oxide. So here they looked at this is the fraction of the CF4 as a function of how much of a fixed hydrogen ratio. So they found a particular ratio where they were able to kind of maximize the deposition. We want to get that deposition because, again, we're trying to prevent any kind of spontaneous etch of the silicon once we get breakthrough of our tantalum. We also want the ability to do just a standard, potentially RIE etch, and then actually do like a post cleanup, because even though I say anisotropic, well, gosh, we're at pretty low ion energies here. How directional are we really? Actually, most anisotropic etches, you do see some sidewall etch. That's actually kind of a research area. So cool. We're going to pick something that's got a certain amount of CF4 to kind of maximize that deposition. We're going to also be pretty happy that there's a lot of hydrogen here because we want more HF formation, less fluorine formation. We want to control the amount of free fluorine to avoid spontaneous overetch into silicon in case we're using this as like a post-treatment. So we've already etched our structures in a standard RIE process. Now we just want to use ALE just to clean up our surfaces and remove that damage. In our case, we're actually just doing all our full etches with the ALE process, but others might want to do it differently. And so we already know, like, this approach reduces the silicon etch rate. This has been studied. Awesome. So we're going to pick something from all this work that we've surveyed. And we're going to say, well, there was maximum deposition on silicon at 6.7% CF4, 26.5%-ish hydrogen, and balance argon. We're going to use that. Cool. Now, a little bit different from what people have been doing before. So yes, we're going to modify our surface, but we're also going to deposit a polymer and have some buildup on top of that surface. And then we're going to remove that polymer, which is really easy to remove in argon, and then also remove the modified surface, but without damaging the underlying material. So we went ahead and did this with niobium, and you can see the process parameters at the top here. And as you can see on the left, let's look at RF bias on the x-axis, etch per cycle on the y, and where it says negative, that's deposition. So at first, depending on our process parameters, we actually do, in fact, get deposition. We're not removing material very quickly. So that's kind of our deposition regime. Then as we increase the RF bias, we get into this ALE window and we start to see a smooth, level etch per cycle as a function of bias. Once we increase the bias enough, we're just back into a physical sputtering regime. That's too high for us. That's not where we want to be. We also look at this on the upper right here as a function of dose time. So we want something where our etch per cycle is stable as a function of dose. So it's a self-limiting ALE process. Well, we found we had saturation at about 1 second. Similarly, on the lower right, we want something where that etch time, we're not getting continued spontaneous etch. Similarly, if we're too low, we don't do enough etch time, we're still in this polymer removal stage. We don't even really get etch. However, and if we get really high, actually, with a really, really long dose, we have found crazy chamber effects that have caused problems. So there's a really nice regime kind of in the middle where if we have a 1 second dose and just enough etch time, we get a very stable self-saturating process, self-limiting process. We found our best process got us about 0.23 nanometers per cycle at a 1 second dose, 5 second etch. For a 16-second cycle time, this is all niobium, 87% synergy, and we did see a roughness reduction. Similarly, when we do tantalum ALE, we saw kind of a similar result ultimately. We actually used the same process at the end, ended up being the best for us. And as you can see, within error, it was the same etch per cycle. But in this case, for reasons we never quite worked out, the synergy was considerably higher. That's something we would like to investigate in the future. And we also saw that smoothing effect. This was actually our first paper ever, so you can see the reference on the lower right. Um, so we went and compared this to reactive ion etch, and as you can see, in the case of niobium, tantalum, and for silicon, it didn't really make much difference. Um, RIE increased the surface roughness in all cases. Now, we didn't really optimize our RIE very much, but in the ALE case, we found that in all cases in ALE, for all the processes that we sort of thought were worthy of doing some AFM, we saw reduced surface roughness. So this is pretty promising. We also looked at the selectivity thing. As I mentioned before, we cared a lot about that. And we even compared what that selectivity looked like for different chemistries. So we found that we thought the selectivity was pretty reasonable, actually. It's important to note the silicon lattice constant is quite a bit bigger. So I tend to oftentimes think in terms of like multiples of the lattice constant. So on the right, you can see when we used our CF4 hydrogen process, we were very close to 1 lattice constant per cycle for both materials. So really, the silicon is etching a little bit faster, but relative to the lattice constant, it's pretty comparable. So we're really happy with that. And it did outperform the other chemistries that we tried ALE with. So cool. I mentioned before we were interested in crystallinity dependence. So actually, we were making our first devices, and these are our first devices actually under test, are actually just got cooled down in a dilution fridge over the weekend. So we should be getting results soon on real resonators. But we took the same process. We noticed that now when we did our process development, everything was just 80 nanometers of tantalum spud, and all our processes was just on silicon. Well, that actually gives you the beta phase, which is a little bit different from the alpha phase of tantalum. When you have a seed layer of niobium, you get more an alpha phase, different crystallinity of tantalum. So we actually found a surprising to us, we didn't think it would be, we weren't sure the ALE was going to show it, but we actually saw a difference in the etch per cycle. We saw a decreased etch per cycle when we had the alpha phase tantalum, and that was verified in XRD that it was in fact alpha phase. So we thought this was pretty interesting, that this ALE process is actually sensitive, it seems, to the metal film crystal structure. Another thing that we're doing right now, we're just starting on ALE of aluminum. And so our approach here is a little bit different. We actually tried to form TMA, trimethyl aluminum, as an etch product for quite a while. Didn't work out, actually didn't really get any etch from that. But we'd had this idea in the back of our minds for a long time about, well, we don't want to just physically sputter aluminum, but if we could make aluminum oxide, that might be really interesting because that's a pretty hard material to sputter. And maybe there's a way that we can modify that if we can control the aluminum oxide thickness and then modify that controlled layer, not all the way into the aluminum, but a little bit, and then remove that modified bit and just kind of have this 3-cycle process where we're oxidizing the surface, modifying it, in this case with CF4, and then removing just that modified bit and doing that cyclically. We might be in a good place. Maybe that'll work out. And this was informed by work by Nick Chittick out of TU Eindhoven, who's now at Oxford Instruments, actually. And Nick had observed, and I think the George group observed something similar in the past as well, that the sputter yield for fluorinated aluminum oxide is quite a bit higher than the sputter yield for aluminum oxides. This was kind of interesting. And we did go ahead over the last few weeks and get some preliminary data on this. And we found indeed that if you look, we're just talking about the step sequence for right now. In these initial experiments, it turns out our ICP power was too high. But if you just do the oxygen step, you just do the physical etch, you just do CF4, they're all kind of the same within error. We also then tried, all right, well, let's try CF4 hydrogen because we thought, oh, well, maybe there's something like HF type effect, or we don't want to have too much fluorine. And it went up a little bit, but not that much, and possibly because there was an undersupply of fluorine radicals. Well, so when we actually got rid of the hydrogen then, and used this argon oxygen CF4 process, we saw a pretty significant enhancement in the etch per cycle. Now we've gone ahead and just begun over the last couple of weeks here uh, using lower ICP power and optimizing this a little bit more. And you can see that we were able to get our physical etch rate to 0, essentially. We don't see any etch. And then when we put the chemistry back in with that same amount of bias and everything else, now we see the etch again. So this is a process that we're pretty excited about that we think could applications for qubits. So there's a ton of work to do with this, but I don't really want to, bore you with all that. We'll be doing stuff over and over for a long time. So let's talk about quantum photonics in the last 10 minutes or so here, and how ALE can be relevant there. Photonic quantum computing's pretty wild stuff. It's measurement based. It's a whole different approach to quantum computing from superconducting. They're computationally equivalent, but the implementations are very, very different. As kind of a device person, the way I think of it, I've got a single photon emitter. Yeah, people use lasers and things, but ultimately you'd love to have that heterogeneously integrated somehow. That single photon emitter I showed you at the beginning has some line width broadening due to etched interfaces, right? These will typically be your gallium arsenide, your indium gallium arsenide, materials like that that are used for these single photon emitters. I also will have some kind of electro-optic modulator that will do my my gates. Frequently, lithium niobate, people use other things, silicon nitride. The challenges here with lithium niobate in particular is you get this non-vertical sidewall profile, sidewall roughness, damage. It's a tough thing to etch. People have done really some incredible stuff actually with just ion milling, but it's a tough material to etch. And the other thing that you'll need is you then need to detect the photons at the end, and that's using superconducting nanowire single photon detectors. These are pretty interesting. You make really, really thin, like 5 to 10 nanometer thick superconducting films on a mirror stack. And when they absorb the photon, you're actually, if you get enough energy absorbed, you'll actually kick this thing above its critical current. Typically, you'll put a little bit of current into the superconducting nanowire. That photon absorption kicks it above the critical current, which breaks the superconductivity, and you see this voltage spike. So they're really just looking for these voltage spikes, but they have to be able to control these things and make these films really, really, really thin, which is very challenging. They have a lot of issues with line edge roughness and other things. So there's a lot of kind of specific fab challenges here. So this is some work that I was involved in with Caltech when I was at Oxford Instruments. Lithium niobate is really tough material to etch, right? But people have been doing this thing called hydrogenation for a while. So you can do hydrogen substitution, and you can get rid of some of that lithium, and you can actually make the material etch much easier. The way people have done this historically is they would just take the lithium niobate, boil it in acid. Now, the problem is that hydrogenation, it's a different kind of material. It's not really what you want. It's not as good as real lithium niobate. And that bulk hydrogenation, or even if you do like a pre-treatment in plasma, it's not so great. It's hard to control the depth of that, right? So this isn't ideal, but it does give us an idea. What if we did a cyclic modification? Maybe we could hydrogenate just the surface in each ALE cycle and then remove that hydrogenated layer. So Austin Minnick's group at Caltech went ahead and did this, and as I said, I was fortunate to be a part of this work. Where they did hydrogen and SF6. And so as you can see on the upper left A here, if you just do hydrogen over and over again, actually you get a little bit of swelling of the surface. SF6, you don't really see anything, but when you start alternating these, you start to see an etch process. And they were able to as well show reduced sidewall roughness, and the material, the XPS shows they weren't getting undue contamination of the material or anything. Of course, hydrogen doesn't really show up in XPS, but they did some work on that as well. So there's all these other approaches to ALE as well. In color centers, this is another area that came up in some work with argon. So Joe Harrimans at Argonne National Lab approached me at some kind of event in Chicago, and he said, I'm really trying to etch like 3 nanometers of diamond and of silicon carbide, and I really want to get. I make these color centers, these atomic scale defects, and the closer they are to the surface, the better sensors they are, because they can get them closer to my things I'm trying to sense. The analytes, these are really nice sensors. They work for all sorts of things. Color centers, generally speaking, there are some quantum memory applications, but mostly at this point in the quantum sensing domain. He said, but it's really tough to etch right up to that point, right, to do these nanometer scale etches. And so I'm interested in atomic layer etch. So it's all right, well, this is pretty interesting. Let's go and look at this. Um, Now, for those of you that don't know, color centers are super interesting. You create this, when they say like diamond NV centers as an example, you actually kick out two carbons, implant a nitrogen, you have one vacancy. It creates this bound state of the defect between your valence and conduction band, and it's pretty cool stuff. So when the spin state is zero, you put red light in, you put green light in, and you'll get a red photon out. You can look at that and monitor it. If you apply an RF field, you can kick this into the +or- 1 spin state, and now there's a non-radiative transmission, so you actually see a dip in the emission. Um, so that's what we're seeing here on the right. As you scan the microwave frequency, um, you can see that when you're on resonance with that transition into the +or- 1 spin state, if you have no magnetic field, you see this dip in emission, right? Because of the non-radiative transition. However, when you then apply a magnetic field, it splits that, and now you actually get two dips depending on the microwave frequency. And so by manipulating this and using pulsing schemes and all sorts of things, you can use this as a really clever magnetic sensor. But again, I'm just a lowly material scientist. That's not for me. I just want to etch things. So we did some work with Julian Michaels when he was at the University of Illinois. This is again, I was at Oxford, and we were this is a project that I was fortunate to be kind of managing. And well, we thought, well, we think that if we use chlorine argon, this could work really well. People hadn't tried it before, and initially we were going to do diamond. For color center, various reasons, we did silicon carbide, which is the other popular color center material, first. Um, and so I said, great, Julian, here it is. We got the project set up and everything. And he went, started doing the work. And he came back to me with these results, and he said, well, I was told, turns out he was trained incorrectly by whoever was the super user. They didn't show him how to take the dose gas out. But I was looking at these results and I'm going, well, these are really nice. And if you don't have to do the purge steps, I mean, you can save some time here. This could work out really, really well. So actually, Julian said, "Oh, I'm just going to keep looking at it then. If we don't need to purge, if we can just bias this thing, just leave everything in and just turn the bias on and off and control the amount of time that that bias is on and look at things like how much chlorine flow do I have and the ratios of things, maybe I can get a really nice etch." And Julian did some really incredible stuff. Um, it turns out that at least for silicon carbide, this works brilliantly. Not only is it a really fast process with just 6-second cycle times, um, but he was able to get 2.5 angstroms per cycle, which it turns out is the size of the dimer, of the silicon carbon dimer. So you're removing, we could never figure out how to remove just silicon or just carbon. We could remove just the dimer. He got 99, essentially enough synergy that he had trouble measuring it, 99, greater than 99% synergy, and incredibly smooth surfaces with this really unique approach. So by being open-minded about, I said it earlier, ALE, it's just you're modifying a surface and removing it. There's a lot of ways to do this. So through his creativity and diligence, Julian was able to create kind of a new approach to this technique. Actually, had been thought about a lot at Houston previously, but they had struggled to get it to work. So it was really cool that Julian was able to kind of make Vince Donnelly's an idea, like take it to fruition. So later, Julian did this on Diamond as well. Diamond has a specific issue where we know, and I was talking about before, how do these devices perform? The surface roughness turns out to matter quite a bit. People do all these really aggressive acid cleanings. Well, Julian was able to modify the same process. Now we went back to the Diamond at the end of his PhD, or maybe the beginning of his postdoc, and was able to show that on Diamond, same stuff happens. Bias pulsed, really fast cycles, and he was able to make what we think is the smoothest piece of diamond ever by basically taking over the tool for a weekend or however long it takes to run 3,000 cycles. And it was able to get incredibly low surface roughness. So that paper was just accepted, and we're really excited to have that out in the public domain soon. So at UNR, we're going to be building on all of this kind of stuff. As I said, our lab's been open less than a year. We're at the beginning. We just got an NSF grant for an Oxford Instruments Plasma Pro ASP. I have to thank Oxford. They do sponsor my research group. as well. We have one graduate student, Ryan Walsh. All that tantalum and niobium stuff was sponsored by Oxford, paid for by Oxford. And it was all performed on one of their tools, the Plasma Pro Cobra. And so we're pretty pumped about this. So we're going to add ALD. The ALD systems are also capable of precursor style isotropic atomic layer etch in these mixed ALD ALE processes, which are really cool because coming from the quantum community, I didn't talk very much about Josephson junctions, but there's some really interesting stuff along the lines of what are called merged element transmons, where we really want to be able to engineer our barrier. I described that kind of native oxide approach before. We want to be able to control that barrier, but it's really tough because ALD, when you grow things, oftentimes, if you want like a 2 nanometer thin film, ALD, due to nucleation delays and such, you'll oftentimes get this kind of island-like growth. So if you can overgrow this and then etch back, and they've shown this in Steve George's group as well as Erwin Kessel's group at TU Eindhoven, you can get really nice, smooth, ultra-thin, pinhole-free films. So this is an area that we think is really, really exciting. And so we've got some proposals that hopefully I'll get submitted in the next 7 days to look at this that we're super excited about. And that's one of the things we want to do in our tool. So wrapping up here, I'm at the University of Nevada, Reno. So on the left here, I'm showing all of these light blue dots. These are big industrial fabs. You will note that none of these dots are in Nevada. Nevada is an awesome place to live. I mean, the amount, I think this winter was a little bit different, but last winter I got 50 days of skiing in. We can see ski runs from town, pretty much from our lab. I mean, it's just an incredible place to live. But we're a little new to this game. So Nevada's got a little bit of ground to cover. And so in the last year, we've had a lot of successes. We've set up the premier fab in the state. Um, so we really have to thank our Senator Jackie Rosen, who managed the appropriations process for us, which got all the funds to get started and actually paid for me for the first 2 years, 2.5 years of this. We've created a consortium, Smart NV. I've done a lot of live television interviews in Nevada, which was interesting. I don't know if anyone's done that, but it's a sort of odd experience. We have our first graduate students. We have students graduating with clean room experience. We're setting up educational programs. And I really, really believe, I think that a lot of us that are in research, that when we're pure scientists, we have maybe a different set of criteria or goals and objectives. But ultimately, the goal of my research and the goal of my lab and the goal of everything that I'm doing is economic development. I care more about economic development for our region than anything else. So I'm really interested in working with companies at every level. As we all know, those of us in the field, economic development, you have to have a workforce to allow companies to come here. And that workforce has to extend at every stage, graduate level, undergrad level, technician level, facilities people, being able to get orbital welding done, you name it. You need that capability in your region. And so I'm focused on this at very much the macro scale. And I've had a lot of great feedback and a lot of great interactions with our governor's office of economic development. So that's something that I'm very interested in talking to people about as well. So with that, thank you. And you can see on the right, we are not done in ALE. There's a lot more to do. So yeah, thanks everybody.
Thank you so much. That was a fantastic talk. I'm going to go ahead and jump into questions. I have some pulled up in the live question and answer session, and I have some that were submitted ahead of time. So please, everyone, feel free to keep putting your questions into the Q&A section. So starting off, I really like this question from Ali Azimi, which is, how can how can we be sure that we use enough energy that does not have physical etching, milling, but the energy is high enough for the surface reaction? Is there a practical method to know what your max power is?
Yeah, so I mean, I really wish that we could just use molecular dynamics modeling for this and just not have to run experiments. David Graves, who might be on today, I don't know. Uh, David does probably the best work in the world in that area, trying to look at what energies do we need, how do we can from a modeling perspective, and has really changed our understanding of some of these processes as a result. In practice, we run it without the chemistry, and I think you saw a few examples of that today. Um, but we just have to run the experiments. And believe me, my grad students run a lot of experiments.
I do believe you. So this one was uh, submitted ahead of time. So plasma enhanced ALE and thermal ALE, what do you see as being the future?
So that's an awesome question. And the reason is because we don't, it's going to depend on the application. So I'm going to go back to my long list of kind of research areas. But on the bottom, I mentioned ion-free ALE. So if it's all about controlling damage, then at some level, for some types of devices, any ions could be deleterious, right? Any ions, you can get ion damage. Um, we're really excited about some like hydrogen SF6 processes were used developed at Caltech and kind of with TU Eindhoven, where they'll oxidize a surface and then use an hydrogen SF6 mixture to get HF in the plasma, which kind of mimics these thermal processes. But in that case, you still are generating ions and you still have other stuff going on. So I think it really depends. If you can use a plasma, they'll often be faster. You might be able to do it at lower temperature. All the advantages of plasmas that we have for so many other deposition techniques and etch techniques. But there's probably a lower bound to how low the damage can be with a plasma that is different from that lower bound that you'll hit with thermal ALE. The other advantage of plasma, however, is when you have a thermal budget. So a lot of the thermal processes will be at 300 Celsius or something like that. In the superconducting qubit community, as an example, people do not want especially their Josephson junction at 300 Celsius. Like they will not stand for it. So it's just application by application.
That's a really fantastic answer. The kind of pros and cons that you have to consider.
Yeah.
So this is another live question from Catherine Young, which is how are you measuring the thicknesses? The films themselves often have some variation across the surface before etching, so I'm wondering how you are measuring such a low thickness change after etching.
Yeah. So first off, all of our experiments are done over many cycles. So we don't run one cycle and then measure thickness. And realistically, if the thickness change is less than about 10 nanometers or so, the students will just rerun it with more cycles. You can actually get into certain things with cycle dependencies, but I'm going to hold off on that for now. So we'll generally run 80 cycles as our standard in our lab. If you're getting a quarter nanometer or so etch per cycle, that's going to give you about 20 nanometers, and we'll measure that in a profilometer. So we do photolithography, pattern our samples, um, do a wet strip. We've learned not to run the Asher because that does actually seem to screw up our results. Do a wet strip of the photoresist and then measure it in a profilometer. And we're glad we actually spent our money on a nice profilometer because it's made it easier. And we do like, I think it's like a minimum of five. They're doing 5 different wafer locations, and I think they do a couple measurements per spot as well. The students spend a lot of time on the profilometer.
Do you see any sidewall etching on that, or have you measured any of that?
So we're really interested in this. We actually have a user proposal at Lawrence Berkeley National Lab at the Molecular Foundry. We actually just got to serve on the proposal review board last week, which was kind of fun. Um, and for that, we only have it's Nevada. We do not have EBL, but they do. So we're going to be patterning really small structures and looking at the lateral etch with EBL. That's actually work we hope to do this summer. Turns out my students had too many classes this semester to do that during the semester. So that was a little delayed on account of I apparently can't take them out of school for a week.
Yep, that makes sense.
Yeah, I was bummed.
So then let's see. Oh, no, not gonna type the answer. So, Jiho Yoon said, "Thank you so much for the nice talk. I have a question about tantalum ALE. As far as I understand, the ALE etch per cycle will vary depending on crystalline orientation of the material, silicon 100 versus silicon 111 due to surface binding, energy packing, etc. Any comment on tantalum? Thickness of the film, can it be grown alpha beta? Do you see a difference in the etch per cycle?
Yeah, so actually that was because we were making these devices that are being measured by Nick Zhalev's group at University of Oregon, and that's exactly what we saw. We did all our development on beta tantalum, which is tantalum. It just sputtered on silicon. These are all sputtered films. And then when we went to make the device, of course, we wanted alpha tantalum, like everybody in the field does. You can do that at super high temperatures. Again, this is Nevada. I do not have Princeton. Princeton's my undergrad, actually. They have a wonderful sputter. They can do crazy stuff. My sputter is super robust and works every time, but it can't go to like 600 Celsius. So uh, we got our alpha tantalum by sputtering on niobium, and then yeah, we went and did it. Uh, we under-etched, and we under-etched, we think, because of the difference in crystallinity. We went back and confirmed that, and it was reproducible. So absolutely. I didn't actually think it would matter that much, but it did. So we had to redo all our samples. Or rather, they did. Brian did. I don't do anything.
Fantastic. So I do see that we are at the top of the hour again, and so I want to be very mindful of everyone's time and thank everyone for attending, and huge thank you to Russ for the fantastic presentation and the whole AVS team that has made this possible.
My email is right there. I'm more than happy to talk about just about anything. We're a new research group. We want to have lots of friends. And come visit us in Reno. It's a beautiful town.
Fantastic. And I think Russ can see the questions, and so I'll make sure if he can't see it that he has them for the future.
Yeah, I think there's some way I can see the questions. It's all covered up on my monitor now.
Thanks everyone for attending. And don't forget to register for AVS. 5 days.
I already did.
Not register, submit your
Oh, we should
abstract.
they're doing we're doing two. We're going to be at AVS, ALD, ALE. We're going to be at AVS. We're going to all those things. So yeah, it's a good show, everybody.
Yep, I'll be there too. I can't wait.